Right, let's look at some spectral analysis for the light that came off our neon gas discharge tube. So there we have it. There's the spectrum there I recorded before. Now the beauty of this app is you can have a look down in the UV, you can have a look in the infrared part of the spectrum. But as I said before, the majority of the action for our neon gas discharge tube was in the red part of the visible spectrum. Okay, and that's why the neon tube looked a very nice orangey red color. Okay, so we're going to look at in a more detail. Now, I did mention this as well. Okay, this is very useful. This is the reference lines. This shows us what we should be seeing for certain elements. Now, it's set on nothing at the moment, but we'd expect hydrogen to give us these lines. We'd expect helium to give us these lines. We'd expect argon to give us these peaks. Okay, that's quite interesting. Argon, right, all the actions in the infrared there. Okay, but we want, there's xenon as well, but we want, and there's mercury. There's sodium. This is interesting. This is why sodium street lamps only give off a very characteristic yellow color. Okay, that's because they give off one wavelength of light. But we want neon, so this is what we're after here. Okay, so these are the lines we should be seeing. Now, what I'm going to do in this video, I'm going to identify the peaks that definitely represents transitions in neon atoms. Okay, I'm going to identify the wavelength for you, and you need to calculate the energy jump the electrons are doing to result in the emission of these photons. Okay, so let's just stretch it out a little bit. Now, the first peak, this is quite interesting. The first peak looks like it shouldn't be there for neon. Okay, now this peak here, it's a very obvious peak. I think it's the second highest. There's nothing there. Now, if we go through our references, we see that mercury has two very definite peaks here. That could well be an impurity of mercury vapor in our neon gas discharge tube. I think that's a very real possibility there, because nothing else fits, but definitely neon does not fit. Maybe nitrogen. Okay, interesting. Okay, maybe nitrogen. A very obvious peak for nitrogen there. So that's possible. So we're going to ignore that one. We're going to ignore that peak. We're only interested in the neons. Now, what do we got here? We've got our first, so we can stretch it there. We've got our first peak here. That looks like that's pretty good. Now, if I identify the actual wavelength, I can bring that down quite nicely. Okay. Now, it looks like it's a bit off there, doesn't it? Okay. Interesting. Right, let's move on to the next one then. What do we got here? I think this one here looks like this one. So let's identify it. Now, the way to identify it is you go for this tool here. Now, we're looking at about 603, aren't we? So if we key in 603, just misses it. Maybe 60, and then we can just move it. Bang on the, there you go, 603.8 nanometers. Okay, I think that's likely to be this peak here. Maybe there's a slight calibration error. Don't know. Anyway, right. So there's the first one to write down: 603.8 nanometers. Okay, this peak looks good. Okay, that looks like it's good. That's about 617. So let's check that. 617 nanometers. Just a bit. Yeah, right about there. 616.1 nanometers. Looks good. Okay, so that's the next one to write down. 616.1 nanometers. The next one, I think we've got a peak here. Okay, So that's looking like it's about 622. Let's check that. 622 nanometers, spot on. Right, so there's your next one to write down, 622 nanometers. Looks like that is the representing a transition in a neon, in the neon atoms. Okay, now this big peak here, this is interesting. There doesn't appear to be anything for neon there. Okay, now if we go through our reference again, maybe there's something there. Maybe there's not. Okay, so that's interesting. Right, what about this peak here? I'm thinking that this peak here is this line here. So maybe 638. So let's go 638 nanometers, a bit more. We can shift that over. Yeah, I think that's pretty close. So 638.7 nanometers. I think that's this line here. Okay, 638.7 nanometers. Looks like it's pretty safe. Okay, now moving on. Any more? Well, nothing else seems to match for neon. Okay, I'm interested in this one here. We've got a very, very big peak, but we're missing it for some reason from ours. Anyway, what's this peak here? Maybe let's check the references. Mercury looks good, doesn't it? Maybe that's an impurity of mercury vapor. Don't know. Okay. Anyway, there's some wavelengths for you to have a look at. Okay. That looks like we might have also an impurity, a small amount of hydrogen, maybe, in our neon discharge tube as well. So there you have it. A bit of spectral analysis of our neon gas discharge tube. Right, your job is to the wavelengths you've written down is to use that wavelength. I want you to obviously convert it into a value of frequency in hertz, and then find out what the energy is. And I want that amount of energy, please, in electron volts. So just a bit of practice, doing some calculations and converting to electron volts. Okay, thank you very much. Thanks for listening.